Hello, everyone. Good afternoon, and welcome to today's seminar, which is organized by the Students of Sustainability at KAUST. My name is Fadil Al-Mukhtar. I'm a master's student in chemical engineering at KAUST, working in KAUST Catalysis Center. And this seminar was brought to me by Students for Sustainability at KAUST, which is the organizer of the seminar. So this is the second webinar of a 2021 Sustainability Seminar Series. And this seminar is titled Electrochemistry Energy Storage for a Sustainable and Green Future, which will be provided by Professor Husam Alshareef. So to introduce our speaker for today, Professor Husam Alshareef is a professor of Material Science and Engineering at King Abdullah University of Science and Technology, KAUST. He obtained his PhD at North Carolina State University in 1996. Followed by a postdoctoral fellowship at Sandia National Laboratory in the USA. And he then embarked on a 10-year career in the semiconductor industry, holding many positions at Micron Technology and Texas Instruments. There he worked on developing new materials and new processes for the microelectronics industry. In 2009, he joined KAUST as one of the founding faculties, where he initiated an active research group which focuses on the development of nanomaterial for electronics, sensors, and energy storage devices. He has won the UNDP Undergraduate Fellowship, Seth Bragg Physics Award, NC State Dean's Fellowship, US Department of Education Electronic Materials Fellowship, Sandia Laboratory Postdoctoral Fellowship in 1996. And the Syntec Corporate Excellence Award in 2006, 2 Dow Sustainability Awards in 2011 and 2014, A.H. Schumann Award for Excellence in Energy Research in 2016, and KAUST Inaugural Distinguished Teaching Award in 2018, and the Kuwait Prize for Sustainable and Clean Technologies in 2018. He is also a fellow of the American Physical Society, a fellow of the Royal Society of Chemistry, and in the IEEE, the Institute of Electrical and Electronics Engineers, Distinguished Lecturer in Nanotechnology. He's a highly cited researcher in material science in 2019 and in 2020. He's the author of 450 referred journal articles, and he has nearly 70 issued and pending patents. He served on the editorial board of several international journals. Please welcome with me Professor Husam Alshareef for today's seminar, which is named Electrochemical Energy Storage for a Sustainable Future. Professor Husam, the floor is yours.
Thank you very much, Fadil. Good afternoon, everyone, or good evening, wherever you are. It is really a great pleasure for me to have a chance to give this presentation. And I want to thank Fadil and Iman, who invited me to make this presentation to the Students for Sustainability group. I understood from Iman during our discussion that this is normally distributed to a broad audience, the KAUST community, people who may be in the same field or different fields, or maybe not in the area of material science at all. So I structured this presentation to try to cater to this large variance in the background of the audience. And so the first half will be a very broad, very high level introduction to the area of electrochemical energy storage and how it fits in the overall sustainability theme and how it compares to other areas of energy storage. And then in the second part, I will dig a little bit deeper into material science, talking about batteries and how they work, and finally conclude with just a few samples of work we do in our group. So as Fadil mentioned, this is a talk focused on electrochemical energy storage. So let me begin, okay, by actually thanking my group members. This is a pre-COVID photo, and many of the team members are not shown here. I apologize for this, but I wanted to acknowledge their work and their contributions. They are the ones who really do the work, and a lot of the stuff I'm going to show here is either with their work or slides that they have prepared for me. About our group is in the area of nanomaterials. And we generally are making nanomaterials for three types of applications. One is focused on energy storage, which is the topic of today. And one activity we do is focused on electronics, using nanomaterials in electronics. And also recently we are starting to do some sensors. And our theme is that nanomaterials, small things making a big difference. We develop these materials, not just for the materials themselves, but we actually put them in devices and try to evaluate devices and increasingly focusing on applied research. So when we talk about renewable energy storage, we need to get aligned to what we're talking about. You know, this is an exciting area to be doing material science. There's a lot of activity and a lot of focus on sustainability and trying to find replacements for fossil fuels. And some of these pictures here show you solar, geothermal, wind, bioenergy, and hydroelectric power are some of the things that we are talking about. There's a lot of promise, a lot of potential for these things, and they can indeed have a positive impact on the environment. But there is one factor that is common to all these renewable energy sources, is that actually they are intermittent by nature. For example, talk about solar power, we have the sun during the day, but not at night. And if you talk about wind, it is seasonal. It can vary by day. It can vary from season to season. For this reason, and this is very different from fossil fuels that's burning all the time. For this reason, energy storage becomes a very important factor in trying to construct and build renewable energy systems. So here's an example of solar power from a solar modules that is monitored over time. And it shows that not only do you have variation in the solar power during the day, but also depending on the weather. I see there may be a message here. Let me just check it. Okay, good. So because of this nature of the renewable energy systems that we are talking about, sources that we are talking about, it becomes imperative that we really develop energy storage technologies that can deal with these variations, because your load, what you use at home or what you use in the factory is constant. You need the same electricity every day. And if the sun is not there that day, you still need the same electricity. So that's why energy storage has gained significantly significant attention in the recent years. Then if you look at the way we can store energy, there are really many technologies. These are cartoons. I try to simplify the idea. We can store energy using potential energy, basically carrying a weight, like you see here. This is called pumped hydroelectric, carrying a weight up. You can store potential energy in that weight that you lift up, and then you can release it and you can get that energy back. That's called storage in potential energy. You can think of this, I'll show in a minute, taking water from a river to a top of a mountain and then letting the water go back down. That's again, basically you store that potential energy by lifting the water up, and you gain it when it goes down. You can also store energy in a kinetic energy. You can have what's called a flywheel. This is a disc that's mounted on a high quality bearings that have very little friction, often in vacuum. When you have excess electricity, a lot of solar, let's say during the day, you can spin this wheel at high speed, and when they, in a motor mode, but the same setup, when the sun goes down, you can actually retrieve, basically in a generator mode, you can retrieve the electricity back by the decelerating wheel. You can also store, like you store energy in a spring. Some people, basically some utility companies, they compress air underground, and then when they have excess electricity, but when they have a shortage of electricity, they let this compressed air come out, and that can spin a shaft in between magnets, and basically you have a generator that produces electricity. This topic of today's talk is electrochemical energy storage. You can store electricity in electrochemical reaction, through electrochemical reaction, and that I will talk about for the rest of the presentation. Then you can have chemical energy storage. We know today hydrogen is a hot topic, okay? If you use solar power to split water and generate hydrogen, hydrogen can be used as fuel itself, or it can be converted, for example, to ammonia, and you can transport it and use it also as a source of energy storage. Thermal energy storage, this is now in building. There's different types of those, but think of a material that during the day, during the sun melts, but at night freezes and releases heat that it absorbed during the day. And there's also sophisticated energy storage mechanism involving superconducting coils. If you pass a current in a superconducting material when it's below its critical temperature, that current remains there infinitely. So you could again recoup that current and recoup the stored energy. So in a way, one thing that distinguishes electrochemical energy storage, if you look at all these images, actually electrochemical energy storage has the least moving parts. So usually it's not mechanically involved like the other systems. So this is one advantage for electrochemical energy storage. These are Google images of the different systems I talked about. This is a hydroelectric, basically pump storage, sorry, and this is the flywheel. This is the superconducting system. This is hydrogen storage here. A compressed gas, you see this is a reservoir underground where you put gas there, and this is lithium-ion batteries. These are capacitors, and this is thermal storage. So this is the landscape of energy storage. And then we want to focus on electrochemical energy storage. So one reason that it doesn't have mechanically moving parts is a good one, but there's another reason. Let's take a look at this very common mode of energy storage. This is called pumped hydroelectric energy storage. This is a very simple system, but it's actually in the US, for example, accounts for nearly 96% of the energy stored by utility companies. This is a very simple system. During the day, when there's a lot of electricity or you have an abundance of electricity, you could basically pump water from a sea or from a river or even from a reservoir down here and all the way to the top, okay? Now you have stored the potential energy in this water that you raised up. And when you have a shortage of electricity, you can let this flow back down. This can move a shaft and then between magnets, and then you can actually have a generator and generate electricity. So this particular area is the particular technique is very simple. However, it's not suitable for many countries. Not many countries have water or have mountains or have seas. And also, as I will show you in a minute, this thing has actually very low stored energy density. This is very big area you need, but the amount of energy you store actually and the amount of water you need is actually very, very huge. So let's take a look at this example. This is a mountain in Tennessee in the USA. It's called Mount Raccoon. This is one of the largest pumped hydro storage in the world, sites in the world. And this particular mountain is about 300-meter height. It has a 528-acre surface area, and it stores roughly 36 gigawatt-hour of energy, which is a large amount of energy. However, you actually can store the same amount of energy in a capacitor, electrochemical capacitor, that's 20 times smaller, and even smaller if you use a battery, and you don't need a mountain. So basically the message here is that electrochemical energy storage is very compact compared to what is being used today by utility companies. And in principle, it can replace all these pumped hydro plants in the world anywhere really, because you can be in the middle of a city. You may not have the ability to deploy such a storage system in urban areas, right? However, one of the reasons why this is still used is because it is much cheaper than electrochemical energy storage today because of the price of lithium and other materials. So as prices come down, and they are coming down, then this provides a huge potential of growth for electrochemical energy storage for utility companies. So now that I showed you that electrochemical energy storage is compact, it doesn't have a lot of moving parts. So what kind of devices can we use to store electrochemical energy electrochemically? Really, simply put, batteries and electrochemical capacitors. These are the technologies we are talking about. There are many types of batteries. I list here, I will not read them. Several of them have been commercialized. Zinc manganese oxide batteries are the disposable batteries we all use. This is a $10 billion market. Lead acid batteries, they are used in essentially all fossil fuel driven vehicles. This battery is characterized by its ability to handle high currents. It's called a high rate battery. It's used to start the car. Then the lithium ion batteries, which have taken off and have made electronics what they are today, and now are moving to electric vehicles and grid level storage. And also some other batteries that are also commercially being deployed, and even though they're all technologies, sodium sulfur. Then we can distinguish between what's called a primary and a secondary battery. A primary battery, you use it once and then you throw it away. A secondary battery is essentially rechargeable. So these, when we talk about electrochemical energy storage, these are the devices we are actually talking about. And the application space for these batteries is increasing every day. These are some images I took from Google and from some websites I reference here. It's moving beyond portable electronics. Now we see in vehicles, there's home-based storage, grid level storage, in transport, in ferries, even aviation, and a lot of power tools and portable tools. So the electrochemical energy storage potential is in fact huge. But before we analyze these applications, for those who are not expert, I want to introduce this unit, which I will talk a lot about. It's called the watt hour or the kilowatt hour. This is the unit with which we measure energy. Okay, so it is basically if you have a device that consumes one watt of power and you run it for 1 hour, basically you have used one watt hour of energy. It's equivalent to 3.6 kilojoule. And if you count calories when you eat, 1 watt hour is about 0.86 kilocalorie. Okay. Another reference point, if you have a 40-watt light bulb in your home that runs for a whole day, it would actually consume 1 kilowatt hour of energy. An average home, this is in the US, consumes about 1,000 kilowatt hour per month. And 1 barrel of oil, since we produce a lot of oil here, is roughly 1,700 kilowatt hour of energy. And the largest electric grid-based battery storage project in the world today is about 1,000 megawatt hour, okay, which is equivalent to 588 barrels of oil. This is just to give you a feel. This is just, when we buy things, we talk about dollars. When we talk about energy storage, we use this unit. And this also can be normalized to the mass of the battery and the size of the battery. So often you'll see watt hour per kilogram or kilowatt hour per kilogram or kilowatt hour per liter. And the energy storage in the battery, its capacity and times the voltage. Both of these depend on the materials. This is where the material science comes in. By designing the right material, you can control the capacity and you can control the voltage. And by multiplying these two, you can get large energy storage. So the better capacity your material has, the larger voltage window your material has, the more energy you can store. And the power is simply the energy divided by time, okay? So this is a very important point to grasp as we talk and analyze these applications. So let's talk about the different applications. So I showed you in that previous image, different applications for batteries or electrochemical energy storage devices. They go from portable electronics to automobiles, electrical vehicles, to trains, and to grid level storage. They go from milliwatt to watt hour, kilowatt hour, and megawatt hour. And then oil is massive. We're talking gigawatt. And then so here's examples. Your iPhone 12, if you have the 5G model, is actually a 10.78 watt hour battery. This is how much energy it uses. Tesla's power wall system, which is a home-based storage system that mounts on your wall, is a 6.4 kilowatt hour. Tesla Model S60 has a battery of only 60 kilowatt hour. Of course, there are larger models, and you can see here this is the range where the electric vehicles are in. And the largest grid project is 100 megawatt hour. There's another parameter that often you find on batteries, which I mentioned, is the capacity. Okay, so in stored energy is the capacity times voltage. So the capacity is measured in amp hours or Ah. And here are the range of capacities for the different applications. So if you look at your iPhone, if you have iPhone 12, it has a capacity of 2.8 amp hour. So they range from milliamp hour for these thin film batteries that used in medical patches or smart cards, 100 milliamp hour for your wearables, 1 to 2 amp hours for your phone, 100 amp hours for your car, and then above kilo amp hour for utility vehicles. So consumer electronics, this is no surprise to anybody. They have been enabled and really by lithium-ion battery. Now we enjoy a lot of portable devices and gadgets and wearables, and the success of these really is no small part is due to the ability to have these lithium-ion batteries that are compact and they can last long. This is projections from Data Bridge market research firm. They're showing this market will continue to grow and basically will reach roughly $17 billion by 2027 just for batteries. Okay, and this is not the only market that really is driving electrochemical energy storage. We all know about electric cars. They are so cool, and there's a revolution going on across the world producing electric vehicles. I'm not going to read why they are, advantageous, but certainly they're good for the environment, and they have low operating costs. And these are projections showing the number of vehicles that will be produced. This is from Bloomberg, and showing the number of vehicles that will be produced by year, and also showing not the number of vehicles, but the amount of battery storage capacity that we will need for these cars. So you see, these are massive growth curves, and it is expected that the electric vehicle demand for battery will exceed those of portable electronics in a few years, just a couple of years. But there are issues with these cars that require the material scientists to get involved. Number one, the limited range. One would like to really have as much a range for the on one charge for the electric vehicle as possible. There's a psychological term for this called range anxiety. Some people are worried that they're going to run out of battery. So there is a big drive to increase the size, the capacity of the battery to increase the range of the car. Also, currently, if you use your home to charge your car, it takes several hours to do it. And this is not acceptable. So we need high rate materials to do charge the battery at high speed. The cars have high initial costs, so we should basically drive down the cost of the batteries, and we need to improve the lifetime of the battery so that we don't have to replace the battery pack every few years. It's expensive. It's a large expense of the car. Here's a graph that shows the range of the car that you could achieve if you increase the capacity of the battery. Again, now we are back to watt-hour per kilogram. If you increase your capacity from 200 to 250 watt-hour per kilogram to, let's say, 400 to 500, you can essentially reach 800 kilometer range. So there's a correlation between having a high energy density or high capacity and high energy density battery and how much you can drive your car. And to do this, we will need basically better materials. This is an area where material science can really contribute. Another worry I mentioned is that how fast does it take to charge the car? So according to US Department of Energy, they would like to have a 15-minute charge for a 250-mile car and using a 300 kilowatt DC power source by 2023. Now, how fast you charge your car battery depends on several things. Your charging source, whether you do it from home or you have 120 volt or 240 volts, and whether your battery can take the ultra fast charging speed. You need to make sure the materials in your battery can take it, because if you overdo it, then you will cut down the lifetime of the battery. So there are different levels of charging speeds that people talk about. I will not read this there, but the detail, but they're called level 1, level 2, fast charger, and Tesla supercharger, and extreme fast charging. If you focus with me for a second on this curve on the right-hand side, you will see that these things are on the x-axis, level 1, level 2, fast charger, Tesla charger, and XFC, the extreme fast charging. And you will see the charging power on the y-axis and the time to charge. This orange curve with the dots is the time to charge. So you see the time to charge your vehicle, this is in hours, goes down very fast if you are able to use an ultra-fast charger, okay? But the requisite thing here is that your material has to be able to withstand it. If you put the wrong material there, then your battery, if you subject it to this fast charging and discharging rate, it will actually degrade its lifetime. So if this is home, in this box right here, this is level 1 and level 2, this is what we might be able to do at our home. Right now, if you do it, charge your car, an electric car in your home, it's taken a few hours, but if you can go back to up in charging speed to these new charging stations, provided the material in your battery can take it, then you can cut down to required 15 minutes in principle. And there's been significant progress recently in this area. So this again relies on material scientists to develop high rate materials. This is another driver for the growth in electrochemical energy storage. This is called the power wall. This is from Tesla. Basically, again, if you have a solar roof in your home, you're going to need some battery storage. You basically cannot do without one. And there are different companies that are supplying these. This is a Tesla unit. Okay, it's a 3.3 kilowatt unit for 2 hours, or 6.4 kilowatt hour. This is an LG Chem. It's a 6.5 kilowatt hour. So these are already commercialized. You can buy them, and Tesla sells them. This is another driver. It's a smaller driver than the car or the grid storage, but it is a driver for that market. And finally, for grid level storage, we also require sizable battery, larger than the batteries that we have in the cars, and larger than batteries we have in portables, certainly. But to deploy electrochemical energy storage, particularly lithium-ion batteries, in these sort of applications, the prices really need to come down a lot, okay? So we need to be able to increase the capacity of the batteries, increase the cost of the batteries, and this will cause this market to grow up faster than it has been growing. I should note that not all projects that are being done nowadays for grid level storage are relying on lithium-ion batteries. There are other battery technologies. For example, sodium sulfur, which was invented in the 60s, it still actually is a favorite battery. And there are several projects around the world I will show you that are using that battery. Here I listed for you the largest grid level storage projects, energy storage projects based on lithium-ion battery in the world. Again, I will not read them, but if you look at their level, the largest one, which is just was announced August last year in San Diego, is about 250 megawatt. And if you assume it's going to run for 4 hours, okay, this is about 1,000 megawatt, so 1 gigawatt. Now, if you compare that to the pumped hydro, not hydroelectric, this should be pumped hydro plant of 30 gigawatt hour, you realize that we are actually in the large scheme of things, this is still a small amount of energy storage. So here, global electricity storage, actually using this approach with lithium-ion battery, grew only by 8 gigawatt hour between 2017 and 2018. Again, you know, and you compare that to the pumped hydro plant, which is 30 gigawatt hour, you see that this is small stuff. So there's a lot of room, a lot of potential for growth in this area, provided the prices can come down. These are the sodium sulfur batteries. They are cheaper than the lithium-ion batteries. There are many plants around the world. Mostly they are small, but there's one in Abu Dhabi here, and there's one in Japan. They are quite sizable, actually. This one is 648 megawatt hour, and this one is 1.5, 1,500 megawatt hour. So these are the largest in the world. This technology has a long lifetime. It has a lower energy density than lithium, but it is a lower cost, and it is a longer lifetime battery. So it has been adopted by many places around the world. So in summary, we see that the demand for this electrochemical energy storage, this is particularly for lithium-ion battery, is expected to continue to grow and to grow a lot. For automobiles and electric cars, it will soon overtake actually the portables. But for storage at the stationary storage, for grid level storage, there's a lot of room for growth and improvement. And this is going to be driven mostly by reducing the cost of these batteries. Financially, you can talk about dollar amounts. The size of this market, predicted again by Bloomberg, is expected to hit $548 billion will be invested by 2050 in this market. And in fact, this might be conservative. We will see, but it's a huge market and it's expected to grow. Now, you know, there's something called economy of scale. When you first make something, it's very expensive, but as you start producing more of it, what will happen is that the price drops. And this is really luckily happening with the batteries. This has different colors because there are different components to the energy storage system. But if you look at the black part of this one, which is the battery pack, you see the price in dollars per kilowatt hour has been steadily dropping. And we are now about 125. We expect it to be at $125 per kilowatt hour in 2025. Now in 2021, we're about 150. Still, people say this is too expensive for a grid level storage, but the trend is going in the right direction. So now I want to switch gears. I hope what I have shown you is that electrochemical energy storage based on batteries has a lot of potential for growth. And I've shown you the market realities of the market for portable electronics, for electric vehicles, for home-based storage, and for grid level storage. Just a high-level overview of what the current state of affairs is and what our projections for the next, let's say, 10, 15 years. Now, I want to focus on batteries and talk a little bit more in detail, dig a little bit one level deeper. Okay, this is the history of battery development. I have color-coded this. The blue color means these are batteries that have been commercialized. Okay, and the yellow, these means batteries that are still under development. And the battery discovery actually dates back to what's called the Baghdad Battery. Okay, so it was discovered 250 BC. This battery, no one really knows what it was used for, but it had a copper cylinder and it had an iron rod there. And between them, it is believed they either had vinegar or fermented grape juice, some kind of citric liquid there, which is really what you need for a battery. Some people think it was used for electrotherapy or electroplating, no known, but this was discovered, and this is really a structure of a battery. In 1800, Volta discovered the zinc copper battery. Okay, these are one of the first ones. And then in 1859, 1866, there were two important discoveries. In France, the rechargeable lead acid battery, which is really the first rechargeable battery. This is used in in all cars that are powered by fossil fuel nowadays. It has the ability, it's a high rate battery, to pass a lot of current, and it's used to start the car. Zinc manganese oxide, this is like the batteries we buy and we use once. These are primary batteries. This is a large market, billions of dollars every year. Then the redox flow batteries, these flow batteries did not really take off. This is a low energy density battery, but it's a long lifetime. It can last for 20 years. It's a liquid based batteries. Some people, you cannot use this in a car, or you cannot use it in an electronics device. This is large in size. It could be used maybe for utility company level of storage, grid level storage. Nickel cadmium and nickel metal hydride were very common in the 60s and the 70s until the lithium ion battery was discovered, and these became obsolete. These used to be in our cordless phones and our portable electronics, but no longer. So in 1992, the lithium-ion battery was developed, and this sodium sulfur I mentioned was discovered in the 60s, and this is still being used. Don't confuse this with the lithium sulfur, I will mention in a minute. And there was a lot of development in the electrolyte of the lithium-ion battery. We went from a liquid electrolyte to a polymer electrolyte, and in 2019, the Nobel Prize in Chemistry was given to the inventors of the lithium-ion battery. Now Tesla is developing new cathodes, and there are a lot of emerging battery technologies I'll mention in a minute that are really going. So this is the history of the battery, where it is today and where it is going. So the batteries come in different shapes. You could have a liquid electrolyte with two solid electrodes, or you could have a solid electrolyte with liquid electrodes. In thin film batteries, you can have all solid, you can have all liquid, and you're going to have even solid, liquid, and gas. So depending on the technology, you could have these variations. This is a famous plot called the Ragoni plot. Usually you plot the power density and the energy density, one on the y-axis and one on the x-axis for your energy storage technology. And this compares them. So ideally you want, this is the fossil fuels like the combustion engine. Ideally you want as high, you want them to be, both of them to be high ideally, but you normally don't get that. Capacitors, for example, down here, they're high power devices, but have very low energy. On the other end of the spectrum, fuel cells here right now, they have high, basically specific energy, energy density, but are lower power. The lithium-ion batteries are right here. These are the sodium sulfur. Thermal storage is like here. So this is a nice kind of plot to give you an overview. The flywheels, these are high power devices, supercapacitors, electrochemical capacitors. They are high power and low energy. So depending on your application, some applications require high power. Then you would come in this area. If you want high energy, no. But what you really want to do is go and see that arrow go in that direction. Ideally, if you could find a battery that will have the same as the fossil fuel energy density and power density, that would be perfect battery. Okay. Now materials, usually if you look at batteries, many of the elements in the batteries are at the top of the periodic table. They are usually light elements here. So you can get large gravimetric energy density. Lithium has the lowest density. So that's a nice feature. They're also small in size, so they're very mobile. Also transition metals, which can exist in multiple oxidation states. So you can have efficient redox reactions are also desirable. And usually, you have compounds that are either oxides, nitrides, or fluoride. Each has its own features. Silicon and aluminum are also used. And I will talk about this in a second. So the lithium-ion battery we have been talking about, let's just dig one level deeper. This is basically a schematic showing what you have. You have this electrolyte in the middle, which has lithium ions surrounded by some molecules from the solvent. You have the anode. The commercial anode nowadays is graphite. And on the right-hand side here, you have the cathode, okay? This is usually some oxide. So these are the reactions that take place during the charge and discharge process. During the charge, the lithium ions go into the graphite. During the discharge, this is when you use the battery to power your devices, they go into the cathode. And so why lithium? Lithium, why people started with lithium? Of course, they tried several things, but lithium has a small size, so it's highly mobile, so it can go into the material and come out very fast. It has a single charge, +1. It means the electrostatic repulsion when it goes inside this cathode is not so high. It has low density, so that means that we can get high gravimetric density. It has the most negative voltage when compared to the standard hydrogen electrode. It means that for a given oxide, when you pick lithium compared to other metals from the periodic table, you get the largest voltage window. And remember, the energy stored by battery is equal to the capacity times the voltage. So if we get a large voltage, we can store large energy. It forms nice interfacial layer. I won't get into this now when you make it. And then it has reversible intercalation. So these are the features that made the lithium attractive. And these are samples of the batteries, how they look like. This is Tesla's battery, and this is batteries you may see in a phone or something like that. The requirements on the electrode materials are actually quite stringent and quite challenging, to be honest with you, compared to other applications that I work with. I mean, I just, if you look at all these requirements, it seems really a challenging task to come up with materials. So number one, your material has to be able to conduct electrons and ions very efficiently, having high electronic and ionic conductivity. And you need to have these oxidizable or reducible metals, which exist with multiple oxidation states. You also need to have some interstitial sites that are not occupied inside the host lattice, the crystal structure of the oxide. So when the lithium comes in, it has a nice place to sit. It's welcome when it comes in. Also, we need to have high capacity. If you're using the material as anode, you want it to have a low potential as close as possible to the redox reaction of the lithium. And if it's a cathode, you want it to have a large voltage. You must not react with the electrolyte and destroy the battery. You have to have it stable structurally, and it has to allow the lithium to go in and out rather quickly. It has to be safe, not catch fire, and not toxic, and it has to be low cost. So this is a lot to ask from a material, you see. And that's why, despite a significant amount of research over the years, the original materials that made the lithium-ion battery a success, the graphite and the oxides, they're still the same today. So there's a lot of studies and a lot of things. It's just the lithium-ion battery has been so optimized with these oxides. But the search continues. And that's why I say this is the material scientist's job, is to try to identify materials that can take us to the next level. If you compare the growth in the energy density of the battery compared to, let's say, the transistor curve, Moore's law, there's no comparison. One looks exponential and one looks flat. And this is the reason why, because finding the right material is a challenging task. So graphite as anode material, graphite is a layered structure, basically looks like this. And then what happens is that lithium ions, during the charge process, they come in the layer of the graphite here. The word intercalated or intercalation means that the atoms can go into this host structure without destroying it. Basically, they may cause a small strain, about 7 or 10%, but they don't destroy the structure. They go in and they come out. And then the capacity, remember I told you energy density is related to capacity for lithium intercalation into graphite, about 372 milliamp hour per gram. On the cathode side, we have oxides mostly, and we are dealing with oxides that have either tunnels like this one for the lithium to go in and out, like this one, so we have planar 2D tunnels. We have this 1D tunnels, and we have these 3D tunnels. So the prerequisite for these oxides to have really an open structure and to be structurally stable, to welcome the lithium and let it in, diffuse in and out fast. And people now with simulations, they can actually predict structures, predict absorption energy of lithium on different structures, and cannot predict or guess what replacement materials may be used. And then also in terms of the voltage of your battery, there's the potential of your anode, in the given electrolyte, and the potential of your cathode. The difference between these two is really what gives you the voltage of the battery. And then the capacity and this voltage multiplied together is what give you the energy right here. However, one thing you have to be careful about is that the electrolyte itself you use has its own potential above which you should not take it. Otherwise, you can degrade it. And that's one issue. So actually for lithium-ion battery, people have identified anode and cathode that will give you 4.7 volt voltage window, but the electrolyte cannot take it. That's why the lithium-ion battery runs much lower than that, 3.7 or 4.1 volts. This is limited by the electrolyte. So if one can develop an electrolyte that can go to 4 or 5 volts, then they can significantly increase the energy density of the lithium-ion battery. And where this potential comes from for a given material, really for the physicists in the group, this comes from essentially the band structure, okay? And then for the chemist, maybe it's basically this, oxidation potential for these with respect to the lithium ions. So you can actually nowadays simulate these structures, look at the density of states for the different orbitals in the oxide, and you can predict which one will have a basically a higher potential and give a wider voltage window battery. So battery development for the future. Okay, so now to go forward, from where we are today, I thought about, okay, how to describe this to you. I think we can break the battery development for the future of energy storage in two different parts. On the one hand, we're talking about incremental changes to take the energy density of the battery beyond what 250 watt-hour per kilogram, let's say 280, 300, which require incremental changes in the lithium-ion battery technology. For example, using different cathodes, I will describe in a second, or doping the graphite with a little bit of silicon, not a lot, just a few atomic percent of silicon, using solid-state batteries, and using lithium sulfur or lithium metal. This is basically lithium-based technologies that can take us beyond 250, possibly up to 400, 450. And then for grid level storage, where we are very sensitive to cost, unless the lithium price can come down significantly, we could potentially develop batteries based on metals or elements that are more abundant in nature, like sodium, like potassium, or develop aqueous batteries or multivalent ion batteries. These are cheaper elements than lithium, or flow batteries, like I mentioned before. So let me just spend a few minutes talking about each one of these approaches. Okay, so for the approach where you still focus on lithium-ion battery, what people are doing right now, and some of these things are really getting close to commercialization. The cathode material has been lithium cobalt oxide for a long time, but that material has issues, in terms of low capacity. It also is can combust. Actually, there's a thermal runaway effect that causes battery fire sometimes. And so playing with the composition of this oxide, there are two electrode materials that are emerging, NCA and NCM. This is basically a combination of three elements: nickel, cobalt, manganese. You play with these ratios and you grade the structure. Okay, you grade the structure. They are not, they're mixed in a certain way. And this can increase potentially the energy density of the battery to 300 watt-hour per kilogram. Another one is to introduce silicon, and I'll show you in a minute why. But in principle, this is the way this is going to work is likely just by not using silicon entirely, but adding a few percent of silicon into graphite. You can get 350 watt-hour per kilogram. Another one was called a solid electrolyte, not using liquid electrolyte. There are some companies doing this. Toyota and big names are doing that. You could reach 450 watt-hour per kilogram. And these are more like future, more problematic batteries, lithium sulfur or lithium oxide. They can take you above 600 watt-hour per kilogram, but many challenges remain. So for NCM and NCA, these are alternate cathode materials to lithium cobalt oxide. This top one is what has been used commercially. NCM and NCA, these are again different ratios of cobalt, nickel, manganese. The NCA is a higher energy density than this one. Tesla is using that in the electric cars, but Tesla is using NCM in the home-based storage because this one is lower energy storage and basically, sorry, this is the one. This is the one that has lower cobalt. So this is the one that has the lower cost. So it can be used in the home. And this is the one that has the higher energy density, so it's used for electric vehicles. Lithium iron phosphate is another emerging material. This one is really advantageous because it uses cheap elements. Iron is rather cheap and it's abundant, but it has low energy density. However, it has high power. So all of these now have been commercialized to some extent. And now people are thinking about the future. They're talking about what's called conversion cathodes. I won't get into this, but these are cathodes that are not so stable, but can in theory give you much higher energy density. The graphite silicon anode, if you look at the silicon here, silicon is supposed to give you above 4,000 milliamp hour per gram. But we cannot really use silicon completely because there's a large volume change. And if you look at the left in this curve down here, you see that from after the first cycle, there's a significant drop in the energy. The battery is not stable. So what people are opting to is a a graphite silicon alloy using up to 10% silicon. This could give 350 watt-hour per kilogram, and many companies are actually working on this. So this is realistic. Solid-state battery could give a 450 watt-hour per kilogram. This is also realistic. Here you use a solid electrolyte, a ceramic electrolyte. It's non-flammable. There's no organics to degrade. And this will allow you to use the lithium. And the lithium, if you look at this, also actually, it's not in here, but it has a very large capacity as well, just like silicon, 3,000 or so. And so there are some issues with this battery. Okay, lithium metal penetration into the solid, large interfacial resistance, and you need to solve those. So nearing commercialization, like I mentioned, some big companies are working on this. Lithium sulfur battery is another type of batteries that people have high hopes for. In principle, it can give you 500, 600 watt-hour per kilogram. And the advantage of this, the price of 1 metric ton of sulfur is $40. But the price of lithium cobalt oxide, which we currently use, is $40 per kilogram. So there's a huge difference in price. And Saudi Arabia has a lot of sulfur. So if one can solve the problems associated with sulfur, which include a lot of problems, really, the conductivity of sulfur is not so high. So you need to add conductive material, and then you lose active material in capacity. Sulfur has large volume change. There's this called shuttle effect. Some of the compounds formed during the operation of the battery dissolved in the electrolyte. They go coat the cathode. They also react with the electrolyte and make it a solid. And then also you have the dendrites that could also potentially form in the lithium. So this is a promising battery with a lot of problems, really. There are some startup companies that are working on it, but I would not say this is like as close as the ones I showed before, like solid state electrolyte. Lithium oxygen battery, again, this in principle can give you 800 to 900 watt-hour per kilogram, but it also is plagued by severe problem, a lot of problems, like polarization is not high, it's not so reversible, it has low reaction kinetics, poor cycle life, and so forth. That's another one you hear a lot about, but the truth is that it has a lot of problems yet. So because of this, so you often now hear about beyond lithium-ion batteries. Okay, lithium is working well nowadays, and there's a lot of future for it. I just want to, like 5 more minutes and I'll be done, talk about why people want to move away from lithium. Why, with the lithium battery is so well optimized, it's worked well for electronics, it's working well for electric vehicles. First of all, I have to say, I'm not sure that anybody is moving from lithium so fast. It's going to be a long while before we do. But if you look far into the future, if really we deploy electrochemical energy storage for all these utility companies and replace all the electric cars, then we're going to hit a point when lithium can become a bottleneck. So lithium has the issue of this fire explosions. In the interest of time, I will not go into all of these. So this is one reason. In some applications, you just cannot use lithium, airplanes or something like that. So it would be nice if one could develop a battery that is more safe than lithium. Second, these are the lithium supplies in the world. There's about 60 to 80 million tons worldwide. And the other thing is that lithium is not uniformly distributed around the world. Sodium is everywhere, but not lithium. So this lack of even geographical distribution makes some countries uncomfortable, and they want to find an alternative battery technology. So today, lithium is not under threat. I mean, there is enough lithium today, but long term, there may be an issue, and that's one reason why people are looking into different battery technologies. So what are they looking into it? For example, sodium-ion batteries. So sodium-ion batteries, this is the price of a ton of sodium carbonate and the price of a ton of lithium carbonate. You go from $150 to $5,000. So this huge price difference, obviously, is big. And Saudi Arabia, since we're in Saudi Arabia, has a lot of sodium as byproduct of the desalination. And so the problem with sodium, however, is that it is bigger, the ion is bigger than that of lithium. So therefore, graphite, which has been the commercialized anode for lithium-ion battery, does not work for sodium. So the people have to develop strategies to make what's called hard carbons, or carbons that is different, or different anodes that have higher capacity to compensate for this. Ourselves, we have been working on this. This is work by Iman and Fan, our group. We are using lasers to coat, polymers directly on the copper collector for the battery, and then we using the laser, we engineer the structure of this carbon, we dope it with nitrogen, and we expand the interlayer spacing. In so doing, she was able to actually get the capacity above 450 milliamp hour per gram. So this is higher than lithium and graphite already. So this is one approach we are taking. Another approach people are taking is using nanostructure two-dimensional materials. If you actually engineer the 2D materials correctly with the right geometry, you can see here in the red curve, we're able to get also large stability for oxide anode now instead of carbon anode. Another approach people are taking is aqueous rechargeable battery. Aqueous batteries are promising. They use liquid water-based electrolyte instead of organic electrolyte. They are environmentally friendly and they are safe because you don't have this fire issue. And also the ionic conductivity is actually higher than an aqueous electrolyte. And when you assemble the battery, if your electrolyte is water-based, you don't need special glove boxes and special room to avoid the oxygen. So this makes manufacturing easy. And a lot of these batteries, they can use these multivalent ions, which can increase your charge storage density. But of course, they have issues. And that is, you can actually have water splitting. And so you use a high voltage. So the voltage, there's a limitation on the voltage you can use. One of the batteries we have been working on is zinc ion batteries. And zinc has a lot of advantages. It has oxidation state of zinc is higher than lithium, but its radius is similar. Although when it's surrounded by the solvent, this may change. Its redox potential compared to standard hydroelectrode is only minus 0.7 compared to the others. So there's less chance of this water splitting issue. It's safe and environmentally friendly. And it has issues like dendritic growth that we have to work on, but its cost is also is competitive. So there's a price advantage, there's a safety advantage, there's environmental friendliness advantage, but you have the issue of the voltage of the battery is kind of low because you are dealing with aqueous electrolyte. So we have been working on oxide cathodes. These are some of the batteries we are developing in our group, getting energy densities that are as high as 352. If you normalize density to the weight of the entire package of this battery, for example, we can get 60 watt-hour per kilogram. Actually, this competes with the lead-acid battery in a car, although the rate performance is inferior still. But in principle, if you can improve that, you can replace maybe one day the lead-acid battery. Another approach we recently developed, this is anode-free zinc ion battery. Basically, there's a lot of problems with the zinc anode in these zinc ion batteries. And what happens is that you form a lot of dendrites. You really underuse the anode. So there's a lot of material that goes to waste. So we are developing this concept. This is early, but we are making some progress on this. This is another approach we're taking. We're working on high power devices, zinc ion capacitors, basically using zinc anode and then using carbon as a cathode. We engineered the carbon, its functional groups, and this allows us to get more capacity. And then these are very stable devices. And we recently also worked on lithium sulfur batteries. My group is developing MaxScenes. These are two-dimensional materials. And we are developing this approach to make these devices with high volumetric energy density. You can see our devices here in the star, right here in the star. They are really competing well with the others. Again, this is looking beyond the lithium-ion batteries. There's still a lot of issues, but we are identifying materials and improving the performance. Finally, my group also works on electrochemical capacitors. These are high-power devices that can be used. This is not for grid storage. These are for wearable devices, sensor networks, and Internet of Things. These are micro devices. We're talking about micropower, not kilowatt hour. But we have been developing some of these devices. You can see here, some of them are wearable, some of them are tandem, and some of them are shown here. And I think this brings me to the end of my talk, and I want to thank all of you for your attention, and I can try to answer some of your questions.
Thank you so much, Professor Husam, for this beneficial talk. I believe we have a number of questions in the Q&A section. There is like a similar question from Raif and from Renzo. They're raising the question that are lithium sulfur batteries better or the lithium ion ones better?
I think if I saw the question, they're talking about the sodium sulfur, not the lithium sulfur, is it? So
yeah.
One of them, okay, so I see these two questions. Let me answer the first one on the sodium sulfur batteries, okay? These sodium sulfur batteries, they were invented actually a long time ago, and they operate at 300 degrees C, and they use a solid electrolyte. And the reason people use them nowadays even though they have lower energy density than the lithium-ion battery, is because they are cheaper, significantly cheaper, and they have a fairly long lifetime. If the price of the lithium-ion batteries can become competitive, people may switch, because of course you don't want to really melt sodium, and you don't want, there's some complications to deal with those as well. But today people go to those because there's a cost advantage and there's a lifetime advantage. Now, with respect to lithium sulfur, lithium sulfur, if I go to, let me go to the, on theoretical grounds, let me go to this, look at this curve. On theoretical grounds, this is basically the curve I'm looking at. You know, the lithium sulfur battery should give you 3,000 watt-hour per kilogram, but even the practical one is about 400 or 500. So the lithium ions, they don't come close. So clearly, if one can solve all the problems of lithium sulfur today, they will use them immediately in electric cars, because today we don't have 400 watt-hour per kilogram. But the problems are just too many. Number one, the sulfur is not conductive. It's somewhat insulating. So you have to add a lot of carbon in the electrode. And now this carbon is not active, so you lose a lot of active material. The sulfur also experiences about 80% volume change. And this particular volume change can also degrade the cathode and the battery lifetime. Then as the battery is charged or discharged, you form these intermediate sulfides that are soluble in the electrolyte. And under concentration gradient, they end up moving to the lithium anode. They can stay there and coat it and render it inactive. They can cause some dendrite formation. And also we can actually turn the liquid electrolyte into solid by reacting with these intermediates. So on paper, the lithium sulfur battery is cheaper, and it is on paper, it has a large energy density, and also sulfur is light, it has a large volumetric density, so it can actually be good for aviation applications. But today's problems are just too many, and that's the situation. Okay, what else? So there is an interesting question that just came in. Okay, I always hear the news about new battery technologies that will disrupt the market, but they never make it to the commercial use. What are the causes for this? So many new potential battery technologies to fail. Okay, this is really an excellent question, and I kind of alluded to this. You know, the lithium-ion battery is so optimized; it's really hard to beat. Yes, there are breakthroughs every day in the newspaper, but in reality, they don't materialize. Let me tell you what in my opinion, at least, where we really stand. So we are looking at this curve now. We are looking at lithium-ion battery. What's happening next? This cathode engineering, it already is commercially available. So this has been a success story. Silicon, there's always stories about silicon being the anode, the dream anode. But the problem, the battery is made purely from silicon anode. They never last, and they never will. 300% volume change is just too much. However, there's a lot of work, but a lot of companies, Samsung, Tesla, and put in a few percent of silicon to graphite. In my opinion, this will one day be commercialized. Okay, there's companies, many startups, tens of them, they're getting a lot of funding. And this one day from the big companies, by the way, from the major automobile makers. So I think a few percent of silicon graphite or silicon oxide is really reasonable. Solid state batteries, Toyota, QuantumScape. Yesterday there was news in Volkswagen is making significant expansion, and they have solid state batteries in the roadmap. I believe this is real. The lithium sulfur, lithium oxygen, I think they have a lot of problems, and who knows when they will make it. So, but these three from the lithium-ion battery point of view are good. Now, other battery technologies like reflow batteries, there are good reflow batteries, and there are companies that sell them today. The problem is that they are 1/10 the energy density of the lithium-ion battery. So if the lithium-ion battery price keeps going down, these batteries, even the sodium sulfur that is being used today, they cannot compete. So a lot of people are trying to develop in new materials. There's a lot of publications you hear, but the truth is that what is being commercialized, the sodium is still way out there. The potassium is still way out there. Silicon anode by itself is still lithium metal. In the 1990s, the first commercial battery was based on lithium metal. It caught a lot of fire. and it was banned, it was canceled, and then people moved to graphite anode. Now lithium metal is coming back. It also has a lot of challenges, especially if you're concerned about safety. But these three here that I have here, the cathode engineering, the graphite silicon, this is my opinion, I'm just giving my opinion, and this solid state, these will be the next batteries that get commercialized at a large scale. All the other ones, the jury is out. Now there's some zinc air batteries that have been, commercialized. There are some niche markets that require certain things. So that's all I can say. Let me see what other questions we have.
There is also an interesting question that says that thanks you for the talk initially, but it says the known reserve of lithium is around 18 million metric tons with an energy density of 100 to 200 watts per kilogram. The total storage capacity is not going to be enough for our needs. Also, it appears that the recycling.
I can make a comment on this.
Yeah.
So typically you use about 70 grams of lithium per kilowatt hour, if I remember correctly. So in a 100 kilowatt hour battery that Tesla uses, there's about 7 kilograms of lithium. Okay, and I did that calculation actually. Let me see if I have that slide here. Let me just say in the interest of time, if you look at the number of vehicles that we are producing today, and you look at the amount of lithium we are mining today, there is absolutely no problem. If you multiply, all the electronic gadgets and all the kilowatts and then all the cars we are producing today, we don't even come close. You can do it yourself later. Okay, I show you. In 2040, we will basically produce, let's say, 70 million cars, electric cars. Assume they are 100 kilowatt hour battery in each car and multiply 7 kilograms by that, and you will see. Let me see if I can find that slide. I did this just yesterday, actually. Yeah, for example, I can show you this slide. Can you see this slide? Yeah, so I did an example. Tesla lithium-ion batteries, they use 70 gram lithium per kilowatt hour. So if the battery is 100 kilowatt hour, you're using 7 kilograms of lithium in each battery. Okay, so I just took this green curve, which is the projection from Bloomberg for electric vehicles. And it says in 2030, we're going to be using about 700 gigawatt hour. So I did the calculation and I found out that we need to do that. We only need 7,000 tons of lithium per year. But the world today is mining 77,000 tons per year of lithium. So today there's no problem. However, if all the pumped hydro storage I showed you and all the cars, there are 1.2 billion cars in the world. If all of them become electric and all of the pumped hydro become electric, then we will run into a problem for sure. But today and in the foreseeable future up to 2030, it doesn't look like lithium is going to be a problem. Actually, cobalt may end up being a bigger problem than lithium. And then these batteries have more nickel and in some cases more cobalt than lithium. So that's the issue. I don't know if this answers the question. Let me see what else.
There is also a point of that recycling lithium-ion batteries is a challenge. What are your comments?
Yeah, I think this also could help a lot. And there's already several companies that are doing recycling. The recycling can take different form, the pyrolysis or the physical and chemical treatment. That's the dominant one. Basically, you take the battery apart and you take the cathode, okay? Because if you're using graphite anode, most of the lithium is in your cathode. So you take the cathode and with chemical treatments, actually there are companies already that are doing that. You can try to retrieve lithium. This certainly could be one approach and could help us meeting the demand, meeting the lithium supply demand as we grow. So recycling has to improve, and it is happening. There are many startups are doing that. The other thing that actually people can do, some reuse of batteries can take place. For example, in the US, you're allowed to use the battery in a car for I think 5 or 10 years, I can't remember. But after that, it's possible to take that battery and use it in home-based storage. Okay, you don't throw it away. So the lifetime of the battery is longer than the automobile industry is allowing in the USA because they're worried about safety. So a second life, they call this the second life usage of the lithium-ion battery. So between recycling
second life usage, we certainly have to, we can do better. So this is if we become completely electrical, okay, electric vehicle, grid level storage, certainly without recycling, it will be difficult to do it. And also hopefully in 10, 15 years, sodium-based batteries or potassium-based batteries for some application, maybe not in a car because the energy density of a sodium-ion battery is not as high as lithium, but maybe for grid level storage, if the sodium develops enough, we don't need to use all the lithium. You know, sodium is significantly more abundant, I show you, than lithium. So all these factors, recycling, second use, developing sodium and potassium ion batteries or even aqueous batteries for grid level or home-based storage, all of these can help take off the pressure of lithium. And also lithium, by the way, exists a lot in the seawater. It's just difficult and expensive to extract right now, but this is also one direction people can take. Okay, let's see what else. I saw Iman. Did Iman ask a question?
No, she was just responding to the chat.
Okay, there's a question about metal air batteries. What is your question about metal air batteries? Well, you know, they really have great numbers, but right now they have trouble written all over them. I think the only one that I noticed people maybe have commercialized on a small scale is the zinc air battery. The problem of these batteries is reversibility. You know, I showed you here. There's a huge hysteresis in the current state of the art. So I think long term, if someone can find the right catalyst, it's right, but it's not going to be in the next few years. I think they still have a lot of problems to deal with. So my opinion on them is that this is not the time for them. There's still a lot of problems to work out. Maybe in the future, the catalyst is really a very important part of that game, and the reversibility has to really be taken care of. Let's see what else. Yeah, solid state batteries. Solid state batteries are quite close. I think there was an announcement from Toyota a year or so back that they will have a car on solid state battery in 2022. I don't know if this is real. Volkswagen yesterday, they're not going to do it today, but in their roadmap, you know, they're working not only with QuantumScape, but also with Swedish companies that are developing solid state batteries. So I think solid state batteries, they will work now. The electrolytes in solid state, they have lithium ion mobility that is similar to the liquid, but they are much more stable. And I think definitely, in my opinion, this is just my opinion, that they are going to be commercialized. It's just, again, you know, the price and reliability has to make sense. Otherwise, people will just use what works today. They are much different than the lithium air. Lithium air got many more headaches, and they're not close to commercialization, in my opinion. But the solid batteries, the solid state batteries, are definitely much closer to commercialization. Okay, let's see.
There's a question that says Tesla has been switching away from cobalt into nickel. Is it just the price or the cost, or there are other reasons?
There is other reasons. So the NCA, for example, is a higher energy, higher capacity cathode material than the LCO, lithium cobalt oxide. So because it's a higher energy density, then you can, the energy density of the battery in the car allows you to drive longer distance. So cost is always on their mind, but also is the range. Now between NCA and NCM, NCA is a higher energy density, but it's more expensive. I think it has more cobalt. And NC, so they use it in the car because they need the driving range. But the NCM, they use it for the power wall. Even though it's lower energy density than NCA, they use it in the power wall because they're concerned about cost there. What else?
Do you see the possibility of the battery industry being developed in the region here? Things like gigafactories and recycling facilities?
Well, you know, of the mature technologies right now, I mean, see, us in academia, this is the truth. I mean, it is difficult, you know, for us to compete with the standard lithium-ion battery today. And people now are building gigafactories of lithium-ion batteries. But people who own the patents for all these technologies and now open the gigafactory started working and doing the research early on, 20, 30 years ago. So if in the regions we are focusing on the technologies of the future, there can make up a time that we are the ones who own the patents and the IP and develop the experience. I think the government is supporting a lot in these things, and I think there is a possibility. At the current state of affair, most people are building gigafactories from technologies that has already owned by LG Chem or Tesla. People have developed and got involved in the field 20, 30 years ago. We were doing no batteries in this field. Now, the future batteries, there are actually there's a lot of new development in the region, not only at KAUST, but in other regional areas that the future batteries of the future basically could be owned or developed here. There's a much better chance than in the past because we got into the game when lithium-ion battery has already been all but completed in terms of design and in terms of maturity.
So Omar is asking, what are your thoughts on the fluoride battery?
Fluoride battery means with the fluoride cathodes?
I guess, Omar, if you want to raise your hand or talk, you're allowed to do so.
Okay, let's see if there's another question while he writes. Okay.
Yeah, he's saying fluoride as an ion instead of lithium.
Honestly, I don't know much about those, to be honest with you, but fluoride, is very corrosive, so dealing with it is not trivial. I work on vaccines, and we are trying to scale this process up. And one of the problems we are running into is that what to do with all the fluoride or HF. So I cannot make more comment than this, to be honest with you. But this is basically an ion that is not easy to deal with, is my opinion.
There's a question by Gayet. He's saying that one way to prevent dendrite is by adding a separator layer on the electrode. I think Toyota developed a separator material that prevents dendrite growth. Can you comment on how can they prevent dendrite while allowing ion transport at the same time?
Yeah, this is an excellent question. And then the people who have, the lithium metal battery has in a way been reborn recently. Again, it was abandoned in the 90s because of the fire, but people recognize that the lithium metal has a very high capacity. So they started working on it. There are many strategies to actually deal with the lithium dendrites, okay? Many strategies, they involve, we are working on that on ourselves for the zinc ion batteries. They involve doing surface coatings by atomic layer deposition, doing polymer coatings, for example. We are doing some plasma treatments on the surface. We are trying to smooth the surface. We are trying to basically alloy the metal with different alloys. There are many strategies to deal with it, and I'm not sure which one is the best one, to deal with. But this is a tough problem to deal with. This is the truth, and the reason it is a tough problem because these we're dealing with metals that have low melting point and they're not so stable, and there's a reason why the initial generation of these lithium-ion batteries used to catch fire. So there's not a single strategy. I'm not sure what's the most effective strategy. There's a lot of paper, a lot of studies that they show good results, but when you scale things up, I don't know which one will win. Our approach, we work on ALD, and we have good capabilities in vacuum systems in our group. We're working on ALD as a let's say a passivating layer. We get some good results. We're working on polymers. We have some project going on with plasma treatment to smooth out the surface. So all these are good strategies. I am not sure which one, to be honest with you, is the best one. It seems that the alloying approach is also showing good promise. So this is an active area of research, and there's no commercial product that I'm aware of.
Thanks. The last question for today says that what advices or suggestions do you have for students working on batteries? Do you think the advancement in batteries come mostly from academia or industry?
Well, I think both. I mean, the people who won the Nobel Prize, you know, they are a mixture. You know, so Stanley Whittingham was in the University of New York, Stony Brook, I believe, and then also the other professor was at David Goodenough was John Goodenough was at UT Austin and was also in the UK, and the Japanese scientist was in a company. So it was a mixture. One should file a lot of IP. I believe we're lucky at KAUST that when we discover things, we can file IP. If you are interested in this area, I think, of course, you have to start in academia. And I think we are fortunate at KAUST. We have a lot of facilities, a lot of capabilities to get in this area. And then you can go work in the industry. If you're not interested in continuing academia, the industry is hiring a lot of people who have academic training in lithium-ion batteries, because even though we don't have big systems here, but we're doing the exact same thing they're doing in the industry. We are testing with the same way. We are preparing batteries. It's just scaling up when you go there, and then maybe more statistics. So an academic career in a university is a good starting point.
Yeah. Finally, I would like to thank you, Professor Husam, on behalf of Students for Sustainability at KAUST for accepting the invitation and giving
It is my pleasure.
very interesting seminar. You can tell by the number of questions we got and interesting participation from the people. So thank you
very much.
Thank you.
Bye-bye.
Thank you so much. Have a wonderful day, everybody.
Thank you. Bye-bye.